all of you?
Yes.
Okay. So let me start my presentation. First of all, very good evening to all of you. Myself, Dr. Payal from University of Mysore, Karnataka, and I'm working here as a women scientist in Department of Material Science Department. So today I'm going to present. I'm going to talk on the bone dielectric parameters, which will change as a result of change in mineralization or the change in any of the structural parameter in the bone. So for the bone dielectric parameters, we are going to evaluate electrical impedance analyzer. That is a technique which currently I'm working on. So before going into details of all the technique and what technique will let us know about, so I think it is important to have a better understanding of the bone composition and the bone structure, and I think everybody would be aware of the bone composition and structure, but let's have a brief overview over that bone composition, so which consists of the 30% organic matrix, and out of 30%, that organic matrix that consists of 90 to 95%, out of that 30%, 95% is that is collagen, and 70% of the bone tissue, it consists of bone salts, and those bone salts including calcium, phosphorus, potassium, magnesium. All these salts, they combine together and they make a crystal structure, which we call it as hydroxyapatite. So it is very important to have the bone composition, and it has to be in this particular ratio. Under any pathological condition, if this ratio changes, and we know that maybe if we talk of the osteoporosis or the osteopenia, all these pathological conditions, or maybe arthritis. So this composition might change. It changes or it might not change. Another thing which is again very important here is the macroscopic structure of bone and the microscopic structure. So let us first have an understanding of the macroscopic structure here. If all of you can see here in this slide, this is just a diagrammatic representation of how bone looks like and what are the different components. So this is the external portion, and this is a presentation of the long bone. Here we can see the epiphyseal portion, which is spongy one, and it doesn't have that you can say the well-defined structure in comparison to the bone which is in the diaphyseal region, which we call it as a compact bone. So when you can see here in the next diagram, when we enlarge this diaphyseal region or the compact bone region, our bone, it looks like that. So this is how it looks like, and the circular arrangement, this single unit, this we call it as osteon, and it is known as the functional unit of bone, which consists of, you can see here the circular arrangement, we call it as a lamellar arrangement of hydroxy. This is nothing but the circular arrangement of hydroxyapatite and collagen together. So this is how the bone looks at if we see at the microscopic level, our bone, it looks like that. So it is very important to have that proper composition and proper arrangement of this osteon structure, and this structure and the composition that might change under different physiological conditions. So this is bone remodeling, and it's a very important mechanism. It occurs in day-to-day life, and that depends on how the condition of our body is. So this is what it is, nothing but the surface phenomenon, where this particular phenomenon that helps to maintain the integrity of the bone, and how, like, when the, you can say, when the body or when the brain senses that there is lesser calcium in the blood, so what happens, the signal that goes to the brain, and from the brain that comes to the bone, And ultimately, that signal will tell the bone cells. We know that osteoclast, osteoblast, and osteocyte cells, they are there on the bone surface, and they are in the quiescent phase. That is a very silent phase. They won't be activated till the signal that comes from the brain. So whenever there will be a deficiency of calcium in the blood, the signal from the brain that comes to the bone, and the quiescent cells which you can see here in the diagram, they get active, not these get activated, they get just retracted from the surface, removed from the surface, and in place of these cells, osteoclast cells, they come they come up here, and they get absorbed to the bone surface. And what they cause, and what they will do here, as you know that osteoclast, they causes bone resorption. So ultimately they will cause the bone resorption. They will erode the bone from a particular surface from where that they will get attached, and ultimately calcium will get released inside the blood. So after this process, again the bone formation, because that needs to be recovered, so bone formation takes place, and then the mineralization and quiescent phase. So all these phases are important in the bone remodeling. And this process, this bone remodeling, you can say, if there is an imbalance in bone remodeling process, an imbalance can be due to so many reasons. May it be age related, may it be that post-menopausal bone loss, and due to certain medications, or you can say because of the lifestyle. So ultimately, if imbalance that occurs in this remodeling mechanism, which is very important, that leads to osteoporosis. Osteoporosis, that's an advanced condition of bone loss. So it is again, as we all know, that it's a major health concern in the developing countries like India and developed countries. And everybody, they are putting their efforts to circumvent this problem. And this is a major issue. And most of the women, over, you can say 50% of women, they will you can say they are prone to osteoporosis because of that post-menopausal bone loss. So osteopenia, sorry, osteopenia, that is a early stage of bone loss where we can see that bone mineral density changes, that we know in the case of osteoporosis, but that's an advanced stage. So if we want to detect the early stage of bone loss, that in that particular stage it might not happen that bone density will change. So there are few of the parameters, I will discuss it in the next slide, that there are few parameters which are quality bone parameters and which are important for the analysis of osteopenia. Because at times what happens, and we have studied the literature, that at times the clinicians, they won't be able to detect that osteopenic condition, because the bone mineral density, that will remain same if you do the DEXA. That's a very sophisticated technique for the measurement of bone density. So if we go for that, and generally clinicians, they go for that, that is a technique which has been used previously for detecting this bone mineral density. But what happens in the case of osteopenia, apart from, or let's say bone density, it might not change, but there might be change in the structural, or there will be change in the structure of the bone with respect to collagen and hydroxyapatite, how that arrangement changes. And this is what we have deduced a little bit in our study as well, that how the microarchitecture changes in the osteopenic condition. And if at that particular stage, we will be able to detect that loss either in terms of density, if not in terms of structure, then it would be really helpful for we people to reverse that condition. I mean, otherwise we know that this particular condition, it cannot be, I mean, we can just only prevent that, but diagnosis at the early stages might be beneficial in this particular pathological condition. So as I was talking previously regarding the bone quality parameters, these are the bone quality parameters which are future fracture determinants. So these are the three important parameters. The first one is arrangement. Like in the previous slide as well, I've told you that how the collagen and hydroxyapatite, they are arranged. So that osteon structure, and that changes as a result of change in the bone remodeling process. And up to molecular level, we know that so many transcription factors, proteins, there will be change in that particular level. So another thing is the crystalline size. Crystalline, by crystalline, we can say that the hydroxyapatite crystal, which is formed, which forms a major portion of the bone, the crystal, the size is, you can say that is, it has a dimension. It is in nanometer scale. So if that size changes, that size also changes in the early osteopenic condition. That is what we have deduced from our study. And the third that we have not deduced, but that is again one thing, that is bone vasculature. So whenever we talk of the healthy bone, bone vasculature is one important parameter which comes into play. So these three are the parameters which we can say that they can be a future fracture determinants, and they are the bone quality parameters apart from bone mineral density. So let's come that the diagnosing bone health. So the clinicians, they have been using, and they are using, these are the biochemical tests for the detection of bone, and that consists of number of like tartaric resistant acid phosphatase test, and alkaline phosphatase, kidney liver function test, calcium, and all those biochemical estimations, they are there. Apart from that, DEXA, which is dual energy X-ray absorptiometry, that is a sophisticated technique which has been used for the detection of bone mineral density. So the problem now is that early diagnosis, as we as we are saying from time to time, that if we will be able to diagnose that early bone loss, and as in most of the conditions and in most of the cases, what happens that we generally go to the clinicians at a later stage when most of the bone, and they are at that particular stage, they are at that osteoporotic stage. So this particular technique, which we will talk in of further, so that is again, it has a number of, you can say, uh, we can say we can get a number of benefits out of that. That is, it might be able to deduce all these parameters. Still, we are working on this. These are the bone quality parameters. So, and another thing is that this particular technique, that is again cost effective if you compare it with DEXA. And moreover, again, I've told you that DEXA, that will give us the quantity parameter, and this might give us the quality parameter, which can be considered as the early or a better bone quality indicators. So this early diagnosis of bone quality parameters has been considered as a major limitation till date, which we are attempting in our study. So electrical impedance technique, we are using to find out the potential of this particular technique to differentiate between the healthy and the deteriorated bone. This is a uh, you can say, you can see here, this is the electrical impedance analyzer, where these probes are there and we can attach, you can change, I mean, this is, these are the probes and this is the sample holder, where right now we are working on an animal model, but you can just design the probes according to, or design the electrodes according to the human being as well. But still, I mean, as I've said, that we are on those initial stages. So we have just designed it to have the sample for the animal model. And electrical impedance analyzer, as we can say that this is one tool which can provide information at the nano scale, like from nano scale to the macro scale. This much information it can provide. So this particular technique that studies the frequency response of electrical impedance of a material, and therefore it can be applied as a non-invasive material characterization technique. The impedance, it has also been like one application of it has been found in the literature, that this impedance frequency response, it has been used clinically as impedance plethysmography for the measurement of blood flow dynamics in certain diseases, in the vascular diseases where they need to find out the blockage. So this particular, you can say this particular principle has been applied over there as well. So the physical mechanism behind this particular technique is all about how the electrons, how the atoms, and how the cells, they behave in a frequency. Because here we are providing our system, which is, you can say in specific, we are talking of the bone, if you can take any other tissue. So we are providing that alternating current. We are giving alternating current to the system. And then we are just evaluating the dielectrical properties. For example, the capacitance, the conductivity, how those parameters that changes, and all these physical parameters, they are very sensitive. They, you can say, they are very sensitive to the minor changes. And this is what we are trying to find out, that even that minor change happens, whether it is with respect to the composition or it is with respect to the structural alteration, that this particular technique, it should be able to reflect that. So the measured impedance spectra, like we have done that, we have taken the data and we have fitted that data with a particular model. So it may represent an electrical fingerprint of the sample, and then it can provide an insight into its properties and behavior. Fingerprint, why we have said that? Because this, the, you can say the values that can be specific to that particular organ. So that needs to be standardized, and this is what we are doing. And how we can say that this particular technique will stand out, as I've told you earlier as well, that the early stage diagnosis, so that, and the information from this particular technique might be highly informative, because as it is going to give us the quality parameters, the information regarding so many quality parameters, if there is change in one parameter, second parameter, or third parameter. And the very important thing is that it is without radiation source, cost effective, I've told you, and then it is again easy to, transportation is also easy, so it is portable. So as like, just to design that osteopenic model, what we have done, I've just done this overectomy. Overectomy is, as we all know, that's just the removal of ovaries so as to create the overectomized rat model, which is again the basis why I have chosen this model, just to have the basis and just to create a model which should be more like that osteopenic model. So this model, it has been well established earlier, in I think 1990s. So this has been well established, overectomized rat model, where we did overectomy, bilateral surgery, and then we did check the bone resorption markers. We did check the estradiol measurement, because we know after removing the ovaries, estradiol measurements, they will, these levels, they will get down. And another thing is, this is a trap 5B, which is again, we have checked that whether after removing the ovaries, the, the estradiol levels, they have got down, and whether after removing the ovaries, it has caused that bone loss. I mean, otherwise, it is difficult for us to evaluate as such. So we have measured these TRAP 5B levels in the serum, and these TRAP 5B levels, after a certain period, after a period of 3 months in the rat, they were significantly increased. So you can see from here that they were significantly increased in the TRAP 5B. So here we can say that, okay, our model has been established. And once after establishing the model, we have taken out the bones, and then we have done that X-ray diffraction studies to evaluate the crystalline signs that I have told you initially, that these are the quality parameters. So one of the parameter was the crystalline size, which we had done X-ray diffraction studies, and we have evaluated that if you compare the crystalline size of the hydroxyapatite crystal of osteopenic bone, that increased in comparison to the control bone. So the size of the the size of the hydroxyapatite crystal in the osteopenic bone in the postmenopausal condition, that got increased. So that increased, we have shown again. I can show you the scanning electron microscopic slides. So these are the scanning electron micrographs which we have done on the same bones. And this is, you can say here, these are the Haversian canals, and these are nothing but the lamellar arrangement. This is the compact bone, and this is the lamellar arrangement of hydroxyapatite and collagen fibers. So here we cannot differentiate between the hydroxyapatite and collagen fibers. These are together here, but these are the Haversian canals. As I've told you in the diagrammatic representation, that these Haversian canals, they will be there, and around that lamellar arrangement, or we can say that the osteon arrangement, that is there. So this, you can say, this is one osteon, this is another, this is another. So this is how we have just compared it with the control and osteo. This is the picture of, or micrograph of, the control bone, and this is of the osteopenic. So here we took so many micrographs, and we have seen that this there is an enlargement of eversion canal. So this enlargement is there, and that is, again, we can say that it is significant. And from the previous literature also, we have seen that the if the enlargement is there, then of course, to accommodate the bone volume, lot of water will go inside, and ultimately, if that lot of water would be there, then definitely the polarization mechanism. I mean, I will come to here. The polarization, which we are going to evaluate by using electrical impedance analyzer. Because if the Haversian canal that gets bigger, so just to accommodate that volume, water will go inside. So water will, and that means the polarization effect. When you pass on the electric current or pass on the alternating current to that particular tissue, which is having a bigger eversion canal and a volume of water, that water would be more in that particular bone. So that will behave in a different, that will behave in a different manner. The polarization process would entirely be different in that case. So that forms the basis of this particular technique. And again, this is not the micrographs of compact bone, but of the trabecular bone, where we can see the resorbed areas. But here you cannot see the osteon structure, because osteon structure, that kind of arrangement, that is not there in the case of trabecular bone, which is the soft and spongy one. So this is what we have. You can say what we have developed that dispersion model for fitting our data. For fitting our data means we have given the frequency to our tissue, let's say from 50 hertz to 5 megahertz. A lot of data points would be there, 90 to 100, or you can say 200 data points would be there. So how we need to, for that particular, for assessing or for interpretation of that such a huge data, we require some model. Some model should be there. So this is one model which has been used previously by Cole, and it has been designed out of that particular model. So we have put this equation to fit the data, and we have got these parameters which we have related to different bone quality parameters. So, for example, this is the permittivity which we have related to the water and electrolytes. And if the permittivity has increased, because in the next slide I can show you here that if you compare, we have calculated the water content as well. And in the osteopenic bone, the water content that has increased, as we have shown here in the electron micrographs. So this, we can just corroborate these studies that okay, in the Haversian canal has increased. So to accommodate the volume, the water has gone inside. And we have evaluated, we have checked it by the thermal gravimetric analysis by using that particular technique. And what we have seen, that we have found that water content that increases in the case of osteopenic bone. So that water content, that increase in water content, that we can see here, because these are the graphs. I mean, this is the data this is the fitted data which we have acquired out of that electrical impedance data. And this is nothing. If you just correlate this data A with the B, these are the different. This is the control bone. Like these are the two different bones. And if you see that this is the osteopenic and this is the control bone. So if you compare this, the conductivity in the case of osteopenic bone, that increases. That increases because of the increase in polarization mechanism. And another important thing, there are few other parameters as well, that is the permittivity parameter and relative permittivity, which we have correlated it with the how that changes, how the arrangement of osteon that changes. So if that changes, that parameter will change. So like I have published three papers on this, and one paper is in biomechanics. So this is, I mean, how we are still in that initial stages of establishing this particular technique, and by looking at the capability of this particular technique, if established in like precisely in this animal model, definitely it is going to be beneficial for the detection of bone health clinically. And I've presented this particular project in one of the orthopedician from AIMS. He had also suggested me, because at times he just said that the problem happens when there are fusion models, fracture model. In At that particular time, they faces that problem. He said that they faces what kind of problem, that at times the fracture happens. They do that everything for that fracture, and after a certain period of time, let's say for 2 months or so, when they open that bandage, that wouldn't get healed up properly. So he said that if this technique will get established, then it might be helpful for us to detect that bone fusion also. I mean, this is what he suggested, that it might be beneficial if, later on, if we will be able to detect the fusion of bone periodical. That means from the day one to at the end of, let's say, 2 months or 3 months of that fusion period. So this is what he suggested that time, but I was not able to do that particular model, that fracture model. That needs to be done again. That requires a lot of other things as well. So this is what I need to say as of now regarding electrical impedance spectroscopy. Thanks a lot.